Do we have any other presenters with us right now? This will be a good time to check your sounds or your slides. Okay, so it is 9 o'clock JST, and we'd like to start our final session for CMMR. I'm Masaki Matsubara from Yamaha Corporation. I'll be, so this is the AI, machine learning, and electroacoustics for music production and music database and ontology session. I'm Akira from Yamaha. I'll be the chair for the AI, ML, and electroacoustics session, and followed by, and the music database and ontology session will be chaired by Satoshi Tojo. Okay, so we have 5 presentations with us today. We first have 3 presentations on AI, ML, and electroacoustics, and 2 music database and ontology. We will take a quick break in between those 2. The presentations each will be 17 minutes, followed by 8 minutes of questions. And we ask the presenters to keep the time for by themselves. Actually, 18 minutes of presentation followed by 7 minutes QA. So please keep the time yourself. And for the viewers, English transcription is available by pressing the live transcription button. And if you're not speaking, please mute your mic. And please note that all presentations will be archived on our YouTube channel, meaning that if your camera is on, your face may also be archived there. Okay, so then also now, if you have questions, please use the Zoom's raise your hand button during Q&A, or you can ask them at the designated Slack channel, which is 3-paper-7-1 up to 7-5. Okay, and after the entire session, we will have a post-session discussion of about 20 minutes in the Zoom breakout room. So you can enjoy, you can have more deeper involved discussions there. Right, so without further ado, we'll like to go on to the first presentation for today, which is evaluating AI as an assisting tool to create electronic dance music by Christian Fischer, Manuel Reinhardt, and Niklas Bohm. So do we have the presenter with us? Is there a presenter for this? If you're a presenter, please share the screen. Okay.
If you'd like, I'm the second presenter. I can go and maybe we'll pick up the first presenter if that's okay.
Well, why don't we do that? So, okay, so we are going to do a slight change of presentation order. We'll start by our second presenter, WaVAEtable. WaVAEtable synthesis, however one would pronounce that, by Jeremy Hyrkas. So if you will please share your screen, start presentation, that'd be great.
Sounds great. No worries. I don't fully know how to pronounce it either, and I wrote it. So let me get my timer started here. Okay, thanks everyone. Yeah, so I'm Jeremy Hyrkas from the University of California, San Diego, and yeah, I'll be presenting WaVAEtable synthesis or wavetable synthesis using variational autoencoders. So the overview of the project, to give like a high level motivation, I'm interested in AI models that synthesize musical audio, as well as our sort of classic computer synthesis programs that we use to compose and perform real-time synthesis. And really the thrust of this research is looking at ways to incorporate those AI synthesis models into the computer music programs and how we may want to do that. So the specific approach for this project is I'm looking at one type of generative model, which is the variational autoencoder for timbre generation, which I'll explain in a moment, and try to develop methods such that any research out there that fits in this sort of broad category can be integrated into a real-time music system without needing to change the underlying model in any way. And so the larger idea here is to essentially look at this type of AI synthesis model and try to find parallels in that way of synthesis versus the classic computer synthesis algorithms that we know, to try to find out how to couple these two together. So quick background on these. I'm going to probably interchangeably say AI synthesis or generative model. Just if you're not as familiar, I'm talking about the same thing here. I'm talking about generative models, which are statistical models. These days, it's going to usually be neural networks, where the idea is to learn a distribution based on some training data such that you can sample from that distribution to create new examples based on whatever your training data is. And in audio, we have so many examples of these, way too many to go over. I actually am just putting this here to say if you're interested in this type of research and you don't know much about it, refer back to the VOD for this upcoming chapter, which I think is just like an excellent primer. I will specifically go a little bit into autoencoders, so if you're not as familiar, we can all be on the same page, because this is what I'm looking at for this project. So autoencoders are pretty popular. It's actually a very old algorithm, but they're popular for generative models in many domains. How they work is it's a model that learns two sections, an encoder and a decoder. The encoder takes input data and tries to learn an encoding, or we call this also the latent space, such that the decoder can learn to take the latent space, the encoding, and create an output from that encoding. So it's doing also, dimensionality reduction and the idea here is usually to basically learn an equality function. So you want to learn a very good encoding and decoding scheme for your input data. And the reason that these are useful generatively is that once you do this, then you can take your decoder and go into, create your own encodings in the latent space. You'll see this referred to as Z, the variable Z in literature. You provide some encodings and the model will give you new examples based on the training data that it was trained on. And in the wild, you will see a variational autoencoder, usually in generative models, which is like an autoencoder. It is trained slightly differently, and I'm focusing mostly on the generation process here, so I'm not going to go into the details of how it's different. Just if you see that, this is what that is. It's a type of autoencoder, but the underlying functionality for generating examples is the same. You train it, you give it this latent space variable, and it'll give you an example. So what I'm looking at in this paper are what I call timbral autoencoders, which are autoencoders or VAEs that learn the timbre space of an audio training set. So on the bottom of the slide here, I've got an example architecture. This is the CAN autoencoder, which is a nice, it shows you a lot of the synthesis functionality of these models. So you start with an encoding, and what you tend to get out is a single frame per encoding of spectral audio. This spectral audio embeds the timbre that you're trying to learn. And so if you want to synthesize some sound, you will need to create several frames, do phase reconstruction so that you can take the inverse transform and listen to the waveform. And when it's created in this sense, you're usually getting just a cyclic waveform out, because you're getting this single spectral frame per encoding. So this is generally how these work. And the reason you might do this musically is that it might be interesting to you to create new interesting timbres for synthesis ideas, or even do things like timbre interpolation of your training, timbres from your training data. The shortcomings of this, if you wanted to use this in a music system out of the box, well, they, you do tend to get this cyclic waveform. If you have one of these models, it just gives you a single spectral frame for encoding. So you need to think about how to incorporate that musically. These models tend to not synthesize in real time, which is actually mostly the phase reconstruction. The actual generative model is usually fairly fast. And if you don't take special care in these models out of the box, they don't do what we would call timbre and pitch disentangling, where you've got basically, if you think about like a Fourier transform, it gives you timbre, like harmonics and inharmonics, but there's actually pitch embedded in that as well, which you may not want to learn. So there's many, many variations of these in research. There's people look at different spectral representations. Here's a bunch, Mel spectrogram, CQT. There's people that look at doing additional regularization on the latent space. There's models that do this pitch disentanglement either in a supervised or unsupervised fashion. So I'm throwing these out there not because I expect everyone to understand them, but it's just to show you that there's a lot of people that work on improving the synthesis capability of these models to learn these interesting timbre spaces. So I'm looking at this type of model and asking, what would it mean to use this to generate timbres in a real-time music system? What is this way of doing synthesis remind us of that we can leverage it? So out of the gate, the first thing that came to my mind is that we can treat these timbral autoencoders like a type of oscillator. And here's what I mean by that. You have your model, you can specify an encoding, which will give you a certain timbre distribution. And you'll get a spectrogram that because it's sort of static over time, it tends to look like this, which your waveform will give you a sort of a periodic waveform of various harmonics. That you could use that as something like an oscillator in a subtractive synthesis system or anything like that. The drawbacks, of course, would be that again, the synthesis tends to not be done in real time, which is an issue. And if you haven't taken care of that pitch disentanglement in the underlying model, then your encoding here will actually give you a pitch. And we would like to be able to specify the pitch of an oscillator. So that becomes an issue. So my way of getting around this in the most general way is to instead think of the timbral autoencoder as a wavetable generator. And how we can do this is say, we do the same process as before. We get our encoding all the way to a waveform, which we know is a periodic waveform. And we can take that periodic waveform and extract a wavetable from it. What this gives us is that, if the underlying model can't synthesize audio in real time, that's okay, because after we extract wavetables, then we can play those back in real time. And if we do our extraction correctly, then we can do our own pitch control and wavetable synthesis. And I will mention that if you happen to if you're working with one of these models that allows you to specify pitch, they successfully do this pitch disentanglement, but maybe you still want to try this wavetable method because you want to do real-time synthesis and maybe your underlying model doesn't. Doing this pitch disentangling helps the waveform extraction process, which I will go over actually right now. So my method for basically turning these timbral autoencoders into wavetable generators, it's a little bit heuristic, but in my case studies, it tends to work pretty well. And the steps are essentially this. You have your model, you specify an encoding to get yourself a timbre, a waveform essentially. You can't assume that you've got pitch disentangled, so you want to find out what the pitch is of the waveform that you've just generated, the fundamental frequency. You can take that waveform, you can resample that waveform so that the period of the waveform is exactly or basically 512 samples, which for historical reasons is a nice magic number to store as a wavetable in a system such as Max or Pure Data, or way back like C-Sound. 512 samples was like the default wavetable size. Although if you want to, you can generate longer wavetables. To go a little bit more into the details, there's more details in the paper, but the idea here of like why this works and what it looks like is, so you get your waveform from your encoding, you give your encoding to your model, you get your waveform. I use the Librosa implementation of F0 estimate of the probabilistic yin algorithm for F0 estimation. But if your model allows you to specify an F0, then you have that ready to go. And the idea is essentially, we know that the period of our waveform in samples is the sampling rate over the fundamental frequency. And then if we resample it to this new sampling rate that we will set to F0 times 512, then the math will work out such that our new period is exactly 512 samples, which will give us a 512 sample for us to grab as a wavetable. Or you can even get a little bit more specific about how you grab the wavetable, but those details are in the paper. But more importantly, I think it's more interesting and more intuitive or more informative to look at some case studies of how you might go about this method of taking the timbre autoencoder and using it in a music system. So I've got a couple case studies. The first case study, I've got a system that works with Max. So I've got a generic, what I'm calling sort of a generic timbre autoencoder. I trained it, it's included in the paper, but it's not meant to be like a great model. It's the most basic model you can generate where you can give it encoding and get some spectral audio out to sort of stand in for how these models function. And this case study, basically, you generate the wavetables offline, read them into Max, play them back in real time. All communication is done via the file system, so wavetables go to wave files that are read in by Max. And then you can do some real-time synthesis with the model from the autoencoder. So here's a brief video of what that looks like. So in this demo, I'm just generating wavetables based on random selections of the latent space. You might want to actually get in there and get more particular about what the wavetables sound like. We'll get to that in demo 2. So I've generated them, and we've got our Max patch open that's read in the wavetables, and now we can start doing synthesis. And I hope you're hearing sound. Cool. So we can change the wavetable that's being played back across all voices. So these are all different wavetables that we've extracted from our model. We can assign different polyphonic voices to different wavetables. And we can even frequency modulate our playback, so we can get FM synthesis from our wavetables, which is not something we could do with the underlying AI model. So we can do some fun stuff, fun synthesis with our AI model is the basis. Now, like I mentioned, one thing you might want to do is actually get your hands on the model, so to speak, and get into the latent space and find the timbres that you like. So for this case study, I'm using Super Collider. And here, first of all, to try to get at this idea that the method, you can sort of, with minimal effort, hopefully plug and play different types of these models. Now I'm using the CAN autoencoder. So not my own, it's a different, different, better sounding one, I think, for the underlying model. And here what I've got basically is a Super Collider GUI and script so that you can specify the latent parameters, listen back to a wavetable, decide if you like it, and then store it. So now you're sort of interacting directly with the model to get the sounds that you want before you start composing. So now here's a quick video demo of that. So basically, I'm just launching the scripts now. So they're talking to each other over OSC. Launching Super Collider, and soon you'll see the GUI, and you'll see me start listening to wavetables as I start manipulating the latent space. Here, what I'm looking for is timbre differences. So save that one. I'll fast forward the part where I'm trying out all these different latent space parameters and saving some of them just for limited time. So now I've got a handful that I like. I'll play them back here just to hear the ones we've saved. We can do wavetable interpolation. And now all we've been doing is listening for timbres from our model, but now we can, use the power of Super Collider and make ourselves a nice synth def and start writing a little etude where the basis is the audio from our underlying autoencoder. So I'm just trying to show off some of the timbral possibilities. So, so from these case studies, I try to get some insights into how looking at models this way, what it can give to us. So some advantages. So can do real-time synthesis performance, even though, as you saw, these underlying models don't actually synthesize data in real time, which was sort of one of the problems to begin with. These two models that I showed also don't do pitch disentanglement, so you can't actually control the pitch without doing something like this to take care of it. And yeah, the idea is it's flexible enough that if you have a timbral autoencoder that can go from encoding to spectral data, then you can sort of plug and play into this sort of system or this way of doing synthesis. And it even lets you do things like, FM modulate the playback and do things that you can't do in the underlying model. There are some drawbacks or complications. So if you have a more complicated, I haven't seen too many of these, but there are some VAEs that will do even a static encoding to a spectrum that changes over time, then you need to rethink how you might want to incorporate these. And I haven't actually seen one of these yet, but I suspect at one point we will. If you have a VAE that will do this timbre generation with pitch control, with real-time synthesis, then the wavetable part is not as necessary. You can maybe go back to treating it like an oscillator, like I mentioned earlier. That's where it fits in a little more, maybe. So I know we're basically on time here. So just to conclude really quickly what I've shown, what I presented is a framework for rethinking of this type of generative model that people work on as a wavetable generator for real-time synthesis. With a couple proof of concepts in Max Super Collider, I tried to keep it general enough to use other existing models that are out there. And in general, I think this kind of points to an interesting type of research, just looking at different types of generative models and how they synthesize audio, and thinking about how we can fit those in with synthesis models that we already understand to try to figure out how to bridge these gaps more. So, okay, thank you very much.
Hey, thank you so much for the wonderful presentation and the very slick demo. So now we'd like to take questions from our audiences. If you have questions, please write it in the chat in the Zoom, or write and then post on Slack, or raise your hand. Okay. So maybe I'll start. Yeah, so I really think this is a really cool idea, in that you can you can use these deep learning generative methods to use it in like a real-time program like Max and Speed. That's very slick. Yeah. One thing I was wondering is that how would you think about interpolating in the latent space? Because I think one of the power of VAE is in its capability to interpolate really naturally in this timbre space.
Mm-hmm. Yeah, so it's interesting. Well, it's also interesting because I think it really depends on your. I've seen some VAEs that interpolate really cool ways, and sometimes the interpolation is actually it's actually not so good, but it's kind of interesting to see. So it's funny because the wavetable does its own interpolation, but it's really just doing crossfades. The idea, of course, in the VAE is you can get really interesting, not just crossfades, but really interesting timbre interpolations. So the timbre interpolation becomes really difficult if you don't have the pitch disentanglement to begin with, because then you're interpolating pitch and timbre. I think to really do that in a real-time system, I think at that point you probably really do need a model that can do both the pitch disentanglement and the real-time synthesis. If you had such a model, then you could do really cool things in real time. You could attach an LFO to the latent space, right, and wiggle it. Yeah, and at that point, then I would say at that point you should treat that as a cool oscillator and a synthesizer, and the wavetable part probably won't give you as much. Yeah.
I mean, like, for example, like, have you considered like kind of brute forcing it, for example, like assuming like a 2D latent space, kind of just sample over like a small grid?
Sure. So you can do, I mean, it's a little similar to the NSynth model, right? Where what they did is essentially the NSynth Max plugin is actually not doing the neural net in real time because it can't generate stuff fast enough. That they just generate a bunch of examples that are all across the latent space, and they sort of map that to 2D in their visualization, and then what's actually doing under the hood is actually doing crossfade of their samples. But it gives you, like you mentioned, it gives you a lot of points that you can kind of fake it a little bit. The one thing that's a little complicated is that a lot of these models, the latent space does tend to be a lot bigger. You would have to sort of artificially find a way to reduce that latent space to something like 2 or 3 dimensions, because the generative power for a latent space that small becomes really difficult.
Okay, cool, thank you. Do we have any other questions? Okay, so I'll go. So I guess this kind of more relates to like the pitch timbre disentanglement issue, but like when you're designing like a keyboard instrument and sampling like some sound, you would not only just sample one waveform. You would sample, for example, with the piano, like particular octaves, in each octave interval end. So I was wondering, how would you apply this method to be able to create something that sounds temporally consistent across like a wide pitch register? I don't know if I'm framing my question correctly.
Yeah, I understand the question. It's not really something I approach in this method, only because I actually tend to like the more synthetic sounding stuff. It's like an aesthetic choice, but I mean, that is in some ways what the pitch disentangle methods also can try to get at, right? The fact that you play different acoustic instruments at different timbres and at different pitches rather, and it's not like the harmonics all just shift up and down equally. So I again think it's kind of like you mentioned, it gets towards the pitch disentanglement thing. I think it's sort of a separate research problem in some ways. Or I think one way that I conceptualize a style of research is thinking you can do research that does the model improvement in some ways, and then there's another research that involves figuring out how that model fits into synthesis methods. Some people approach them simultaneously, which is very cool, but that can be very difficult to solve all those problems at once. But I guess the answer to your question is I'm not sure that this specific method would take care of that very well, unless the underlying model took care of it well.
I mean, like your demonstration is like, oh, okay, so yeah, I mean, like your demo of using FN, this as like an FM and like using it to trigger an FM and like doing all of these kind of things kind of suggests that that's kind of like the main use case. But actually, yeah, we may have more questions, but unfortunately, the allocated time for the current presentation has now ended. So, okay, so let's give a big round of applause to Jeremy for his wonderful presentation. And
Thank you.
okay, okay, and do we have with us the first presenter for the first presentation evaluating AI as an assisting tool to create EDM?
Yeah,
yes,
actually, I'm here. I'm so sorry. I was late. I mixed it up.
Okay, no, it's no problem. So would you care to actually? Okay, so would you care to do a quick check of screen sharing and sound check if you have any video or audio materials?
I just have a screen, so I can a presentation, so I could share this with you.
Okay.
My keynote is here. 1 second. There. So let's share it. It's over there. Keynote presentation. Does that work?
So yes, so we can see the screen. So now we are going to actually go back to the first presentation then, and
Sure.
we'll have the presentation evaluating AI as an assisting tool to create EDM by Christian Fischer, Manuel Reinhardt, and Niklas Bohm. And the presentation will be Christian.
Yeah.
Okay,
Excellent.
So the stage is all yours.
Thank you very much. Okay, so again,
actually, sorry, I'd
yeah.
like to just quickly interrupt and just say that the presentation will be 18 minutes, followed by 7 minutes of QA, and it will be your responsibility to keep the time. Okay?
Sure.
So
no
now
problem.
the stage is all yours.
Okay, thank you very much. So first of all, I really have to apologize again that I'm late. I mixed it up. I thought it was 2 a.m. my time. Now it's 1 a.m. It's completely entirely my problem and my fault. So I'm really sorry. My apologies for that. So thank you for having us here at the CMMR. My name is Christian Fischer, and the following presentation and so the paper respectively derived out of actually a bachelor thesis here at our Academy of Applied Sciences in Fulda. As I am at the other side of the planet currently, let me kindly mention that Fulda is a town in the very heart of Germany and about an hour car ride northeast from Frankfurt, if you know that city. And our academy has about 10,000 students. Also, let me briefly mention 2 things before I dive into the presentation. First, unfortunately, I am, as you can see, alone here today, as Manuel and Niklas could not be here for several reasons. And second, I personally consider myself neither a specialist in EDM music nor in AI, but the specialists were Manuel and Niklas. So personally, afterwards, if there are questions about AI and EDM, yeah, I guess I cannot be of so much help there, as I am rather into electroacoustics and I'm a sheer user of AI. Still, nevertheless, I guess the conducted research that I will present here today offers some pretty interesting insight into the possible use of AI into, well, let's say the production process of EDM music, or basically any kind of music which is rhythm or melody based computer music, and which you can actually produce in the DAW. So we had 2 questions in the very beginning. First one was, can I use AI to speed up the production process? And the second question was, how do listeners perceive this AI composed music? Do they perceive it in a way differently, for instance? What we did so we used EDM music, which is the genre, which is electronic dance music. We utilized Google Magenta Studio, which is the AI. And in the end, we had, of course, tests and questionnaire, especially regarding the time of the production and, as I mentioned before, how people perceived it. So why did we choose EDM music and nothing else? Well, that's pretty straightforward. In 2015, the International Music Summit's business report estimated that the electronic music industry is worth about $6.9 billion. So it is a pretty huge community, and it has quite a value and quite some impact on the creative industries. And the second big reason why we chose EDM is that it has a pretty repetitive arrangement of melody and rhythm patterns. So there are pattern variations and a comprehensible music structure, as it is, as you can see on this picture, dance music. So which makes it a pretty good subject for research and the use of AI. And the third reason was because it can be produced entirely within a DAW and within the computer. So this means we can track and analyze the whole process of production pretty well. So this is a screenshot of Google Magenta Studio. We chose this one because it is free to use. And Magenta incorporates several research projects within Google, and one studio is one of them, and it serves as an AI support, especially for the digital music production. It works as a standalone, or you can incorporate it as a plugin for a DAW, as you can see here with Ableton, for instance. It utilizes MIDI and is therefore also pretty easy to apply. The second one, the green one, for instance, this Generate one, is one where you can actually really let the AI run on its own. Then, of course, we wanted to address the production process, and which I said before, it's entirely on the PC and therefore easy to monitor and analyze. And what we did there is that we had a look at the composition process, especially of the melody, of chords, of the bass line, and of drums. We excluded mixing and mastering in this work. So the test structure, what did it look like? Well, there was an efficiency evaluation, which means especially the time that is used to produce something, and the listening evaluation with about 50 people that, and we conducted a survey and an online questionnaire. So let's have a look first at the efficiency evaluation. So we did measurements, and what we used for this was basically, we measured the mouse movement, the mouse clicks, and the key usage, utilizing the free software Mousatron. First, in the beginning, 3 simple EDM tracks, according to 3 stages that I mentioned later, were composed, and each of them had bass chords and melody components. In order not to confuse the participants for the later survey by different drums or drum patterns, in those songs we used identical ones for all of them. For the music production itself, we used the digital audio workstation Studio FL on Windows, and the aim was whether we can speed up this production process. So there are 3 levels of impact. We call it inspiration or human production, AI assistance or co-production, or full automation, which means that inspiration means that the human producer is supported maybe by the AI. For example, the AI generates a melody and the producer is inspired by it or uses hardly or even no parts of it. While in the second level, the AI assistance co-production level means that the AI assists human in the creative process, and their bigger parts of the AI generated music can be incorporated into the composition. For instance, by suggesting subsequent notes or something like that. And the third level is that the human producer is completely out of the process, so to speak, and that the AI generates the new music on its own without any kind of input. Also, there are those 4 phases that we figured out were interesting in the production process. First is the kind of preparation phase. So you open the DAW and do all the settings and stuff. Second is the composition phase itself. And then there are 2 phases where you edit your composition and alter it. And the results look like that. So that means that in the preparation phase, human production performed best. The preparation took just about a minute, actually, with both AI and AA automation and assistance took about 3 minutes. In the composition phase, the tendency of the first phase changed a little bit. Here, the human production took by far the longest, about 9 minutes. With the help of AI assistance and AI automation, up to 85% of the time could be saved. In editing phase 1, without mixing and mastering, as I said before, it is noticeable that the AI assistance was particularly high, had particularly high values. To adjust an AI given melody to one's own desires might take time, so that the duration of the process phase was therefore about 4 to 5 times longer for the AI assistance than for the other 2 production types. In the editing phase 2, great inspiration can come from sound design and melody so far. So in this, with the support of the AI, one comes to a time saving about 65% there. But the AI assistance has the lowest effort in this phase. But this could change, of course, if the experiment would be performed several times. So let's have a look at the listening evaluation. So how this music was perceived by our participants. So the second aim of this study was to find out how listeners perceive it and to investigate those. We had a questionnaire for 50 participants with different musical backgrounds and individual tastes in a balanced proportion. And they were asked to fill out an online questionnaire about 3 generated songs. The participants listened to those songs and were asked to rate them according to the following 8 evaluation criteria, which we took from a research conducted in the United States. So there are those criteria like creativity, recognition value, arrangement of tones, cohesiveness, variety of tones, energy, and danceability. And what does this mean? Well, creativity means, does it sound somehow new for the listener? Recognition value means that, does the melody remain in one's mind? The arrangement tackles the structure of the song. The cohesiveness means that, do the different parts of the song fit together or not? The variety of tones means, is it, for instance, monotone or boring, or is it interesting? Energy is one which tackles especially EDM music, because it means that, is there a certain kind of trigger or energy in the music that makes people want to dance? And danceability, and emotion, I guess they explain themselves. Yeah, so the participants could rate the different criteria from 1 to 5 points, 1 meaning low and 5 meaning high. And in the end, all the points from all 50 participants were also added to an overall score for that song. So as we can see, the first song, the automation, was generated by the AI alone, and the creativity of the song was rated with an average in the middle of the scale. The recognition score averaged also with 2.7, and the arrangement was rated 2.76 on the scale. So overall, the song for all 50 participants collected 1,228 points in all criteria, which gives an average value of 3.8 on the scale. The second song, the human production, means that it was entirely produced by humans, and its arrangement scored best with an average of 3.8 points on the scale. And also the cohesiveness and the danceability were pretty okay. The overall score was 1,365, so it's a little, it's higher than the automated song by the AI. And the third song was an AI-assisted song. So it's we could call it a collaboration between the human and the AI. And the creativity received the highest score there with an average of 3.82 on the scale. Yeah, so as a result, as a conclusion of this research, you could say that we expected that the producer would have really significant savings in time and effort by using the AI. But some of the results differed these assumptions. And the experiment showed that the use of the AI in production increased efficiency, especially in the composition phase and in the second editing phase. There were no significant difference in the overall production ratio in the preparation phase, but this phase was slightly faster with human production. Overall, the AI automation was convincing with an efficiency increase of about 40%. AI assistance decreased production efficiency by about 20% on average. So overall, this means that it can be stated that that the introduction of AI into this production process, especially time, yes, can be saved, but for EDM producers, the creative part of the composition process can be aided only to a certain extent. So the efficiency, so when we talk about efficiency, we could say, yes, efficiency, yes, but the creative process, I guess there maybe this could be also a topic for further research. Okay, I guess, I'm still in time, I guess, 17 minutes about, at least to my clock.
Yes, thank you very much. Thank you very much for the interesting presentation. We are going to now, we like to take questions from our audience. So if you have any questions, please either raise your hand in the reaction or please write your questions in the chat.
I need to open the chat then, 1 second. Yes, there is.
Okay, please. So if you don't have any questions, maybe I'll go then. So I was very, very curious about the AI assistance. Have you did you observe any user behavior, change in user behavior, like for example, spending more time doing something, or like changing focus of where the user puts creativity as opposed to human production?
So that the human producer would behave differently when the AI
exactly
assists. Okay. Well, yes and no, because what really happens, and this is also interesting, is that if the AI suggests things, suggests, for instance, subsequent nodes or something, and then you might get inspired as well during the process. so maybe you change your initial plan and do something else because according to what the AI does. But when it comes to efficiency, it's just faster. It doesn't change really your production, but you just start something and the whole process is shorter. But you don't change something in your behavior, so to speak, regarding the technical process itself. But regarding creativity, yes, it changes it because it might really change your initial idea for the song.
I see. Okay, thank you. So basically, like my understanding is that they kind of just focus on similar things, except you'll have different sources of creativity other than yourself.
Exactly.
I see. Do you have any? Okay, good. So, do you have any questions? Other questions from the audience?
In the chat, I can't see any yet. No.
Okay, so maybe I'll one more question. Actually, yeah. So, one question. So, were the users enjoying the experience of AI-assisted composition? This kind of becomes more subjective, but
yeah, sure. But you mean the listeners, the participants in the
producers,
the producers itself? Well, to be honest, it seems sometimes to lack a little freshness, or I don't know how to put it. You know, I personally, well, it depended a little bit. I personally was not convinced all the time, while Niklas, for instance, he was he liked it, you know. So it's hard to tell. It's a very personal perspective, but yeah. So I think personally it lacked a little creativity, and this is also, by the way, what the participants thought when they listened to this music. It lacked a little creativity.
Interesting. Yeah, I mean, I guess it's also like the issue of like UX design of these AI systems. So it's not exactly like, you know, if you have AI assistants, it's not creative, or, you know, people would perceive differently depending on the tools. But, yeah. Okay. So do we have any other questions from the audience? Short one. If not, so I think we'd like to maybe go to our third presentation. So let's give a big round of applause to Christian for the very awesome, inspiring presentation. And
thank you very much.
Thank you. And now we'd like to go to With Love, Electroacoustic Audiovisual and Telematic Music by Paulo, Chagas, and Cássia, Bomfim. So so Christian, would you finish sharing the screen? Yes, thank you. And Paulo, if you...
I'm awaiting that Christian close his camera.
Okay, so yes, now the screen is all yours, Paulo.
Oh, okay, thank you. And I'll share my screen. Oh, wait a minute, just a minute, just a small minute, okay. Let me open the PowerPoint. Okay, so share the screen. Yes, good morning. Can you see my screen?
Yes, we can. Yes,
okay,
and the
good morning. The title of our presentation is With Love, Electroacoustic, Audiovisual and Telematic Music. And I'm Paulo Chagas, and we are presenting together with my partner, Cássia Carrascoza.
Telematic collaboration. What is the energy that connects us? We are reflecting about this model of production and how our experience can contribute to the community of artists and scientists. How we create telematic connections. In this presentation, we are giving an overview of our recent work in the last 2 years that we are doing here, me in São Paulo and Paulo in California, Riverside.
So what is telematic music? Let's look for a definition. So telematic music is an attempt to make a synthesis of two different types of communication. First, the communication of chamber music, which occurs in the physical medium with bodies producing gestures that are translated into sounds. And second, the communication of electronic music, which occurs in the virtual medium with apparatuses producing programs that are translated into sounds and or images. Let's compare traditional music to telematic music. Traditional chamber music is historically structured as a succession of linear events, such as themes and variations. Telematic music creates a dialogue that occurs in simultaneous time and space, and all players in all places make decisions relating to themes and its variations all at once. This was said by Czech philosopher William Flusser. Telematic music offers the possibility to reshape musical performance in virtual spaces by reconstructing the subjectivity with the experience of presence.
Telematic music is a playful game and dialogue. Telematic music is a playful game shaped as a dialogue. Man and machine act as partners, devoting themselves to the systematic generation of information or data. The playful game emancipates man from the controlling functionality of the machine.
So, in order to better understand telematic music, we go back in the history and let's have a historic overview of electroacoustic music. So we see three different branches, or three different processes. One is the Musik konkret, the second one is elektronische Musik, and the third one is digital music. So Musik konkret is connected to the Paris studio in the 50s, and here we see Pierre Schaeffer, which starts to experiment with recording techniques for capturing sounds of the acoustic environment. So with the Musik konkret, sound is released from its cultural references and becomes a self-referential paradigm for composing new audible forms. The aesthetics of Musik konkret develop new phenomenological notions such as sound object and reduced listening. Musik konkret provided electroacoustic composition with analytical and synthetical approaches to sound perception and composition. Now let's turn our attention to elektronische Musik, which is related to the Cologne studio, so which besides I worked there 10 years in the 90s. And as you see here, Karl-Heinz Stockhausen, which is the most famous composer related to the Cologne studio. So, and in the tradition of elektronische Musik, we have the carry on the European serial music. Invented new sounds built from simple elements of technical apparatuses, especially the signal generator and the noise generator. But at the same time, it carries on electroacoustic technology that were developed during the German Third Reich, which radically transformed the public experience of listening while creating new acoustic frames for political activity. This is something very important in the history of all electroacoustic music that has been overlooked. So in third, talking about digital music, so digital system introduced non-linear sound representation. The sound is broken down into atomic dot-like structures that disintegrate into a mosaic of numbers. The fragmented granular structure of sound can then be manipulated by computers and artificial intelligence. Digital music dissolves the connections to the temporal sound tissue. Human agency is replaced by cybernetic agents. So this is the whole, let's say, philosophical background of computer music and artificial intelligence. So let's talk about the electroacoustic paradigm. So the paradigm is a sort of matrix that is related to the idea of Thomas Kuhn, that the science evolves as a paradigm. So then we see here that we have an electroacoustic paradigm. And what is the basic things of the electroacoustic paradigm is that it articulates noise. And it creates a continuous interaction between microscope and macroscope levels of sound organization. It extends sound perception and consciousness. It creates a myriad of sound poetics, such as soundscape, deep listening, etc. But also, it explores the vibration-centered model of sensitivity for other purposes than music. For example, we see a lot in prisons through the world that electroacoustic sound is using for punish and torture. And this is a very, very significant development that is related to electroacoustic sound and music. So let's talk about electroacoustic music composition. How is the cybernetic dialogue shaped? The heterogeneity of sound material is an aesthetical foundation of electroacoustic composition. It requires multiple agents developing specific scientific and artistic competencies so that the dialogue is the basis of the creative process. The dialogue involves the systematic manipulation of apparatuses. So apparatuses is not only hardware, it's also software. The dialogue is a cybernetic game in which human beings and intelligent tools continuously exchange information. The cybernetic dialogue challenges the notion of authorship. This is an important consequence. Instead of an author, the collaboration becomes the transformational power of artistic creativity in the current society. And let's turn our attention to sound embodiment and space. Embodiment and gestural activities are key concepts of music. So music is related to body and to gestural activity, but the increasing focus on the multiple connections between sound, body, and listen shape the discourse of space in electroacoustic music. So music is brought to the body. And then that's the inactive approach. This is an approach of cognition that emphasizes sound not as a representation, but as a process of sense making, which is embodied. This represents a significant shift from the typological and morphological approaches of sound to new formulations based on phenomenological and ecological descriptions. So we saw some of that here in the conference. So, and finally, let's talk about audiovisual music. Why is audiovisual music so important? In the world of electroacoustic music, there is a growing interest in audiovisual composition. More and more electronic works are created in connection to visuals. Audiovisual music addresses a multimodal perception and sensibility. It reveals two important components. First is the convergence of fields and perceptions, image, sound, and many different fields and perceptions. And second, the increasing diversity and differentiation of forms, of artistic forms. Audiovisual has the potential to bring electroacoustic music to a broader audience. But this is the other side of the audiovisual communication, is what we can call audiovisual saturation. The concept of audiovisual arts is framed by the dominant role film and television play in our society. Audiovisual technology creates a myriad of trivial objects and gadgets that take a hold on our existence. Therefore, it's very important to develop a critical reflection on audiovisual communication. We need a comprehensive account of the relation between sound and image beyond the conventional forms of cinema. It's necessary to deconstruct the hegemonic discourse of film and open up to the broad spectrum of possibilities and diversity of audiovisual forms. And now turn the word to Cássia.
Thank you, Paulo. So let's go back to our work. And this is the Mojave Desert in California, where we started working on our first audiovisual and telematic piece composition that we created together. We are very happy to have our piece here in the playlist together with such great other works. And so thank you for this. We went to the desert thinking like building a performance with the soundscape and the landscape, but we didn't have like a plot before. We were just building this narrative. And here, Paulo, you can see he was setting his 3D camera and the Amsonics microphone. And I was trying to work with performance for these machines as well. And just after this started the quarantine and we started working together telematically. From soundscape to telematic immersion, Mojave is a flute, electronics, and 3D video piece. And there are a lot of layers in this performance in the desert. We did a 3D video and Ambisonics audio recordings. I was improvising and interacting with the soundscape, exploring extended techniques for flute and bass flute. Paulo made an electroacoustic composition and also flute composition and live electronics for Max, exploring algorithms of delay and feedback. The audiovisual composition reflects on presence and absence as vectorial forces of creativity. And we had several telematic performances from this work.
Telematic collaboration, creating a global consciousness. Telematic music make possible artistic collaboration between participants in remote locations. That's our case here. I'm in California, she's in São Paulo, and we have been working telematically since 2 years. It facilitates interactive and interdisciplinary art. Telematic music transcends the body, amplifies the mind into unpredictable configurations of thought and creativity. Telematic music connects people and can contribute to the emergence of a global consciousness.
So here we have different works that we were doing together. This is virtual studies. There are pictures from I'm a Voice Without a Form. Those are pieces that Paulo composed, but I was also collaborating with some improvisation or with the body performance. There you can see my place here, where we were dealing with a lot of different technologies, Jack Trip, the software, and also for me it is a very nice form to experience the machine's relation as a flute player, as an artist. Here we created a different version for the same virtual studies. And yes, this piece, Resoundings, it was written this year, 2021, for flute and for orchestra as well. So we had the orchestra recording presentially, and I was playing in the telematic way, always with this video behind me, and we were trying these differences for performance And I feel that it's really different when you perform in this kind of way, that there is a kind of a dream atmosphere, which is really different, a kind of fantastic thing. So that's it.
So telematic embrace, why telematic collaboration is so important? Modern technology has changed our sense of the world as it tends to reduce everything into mere resources, including human beings. This is said by the German philosopher Martin Heidegger. The programmatic magic of technical apparatuses tend to eliminate critical things. We concentrate ourselves in the surface of the apparatuses and we forget to think in the deep level. With modern technology, relations of power move from physical objects to the symbolic level of programs and operators. Telematic communication, however, has the potential to radically transform the way we communicate. The telematic dialogue embodies Flusser's utopia of freedom as a struggle against entropy, which emancipates men from the controlling functionality of the machine.
Telematic paradigm, what connects people? The telematic paradigm involves not only the technology of interaction among human beings, but also the connections between human minds, intelligent systems, and affect. Like gravity, passionate attraction draws together human beings and connects them. Love is the key of the telematic paradigm.
Yes, with love. Why love is the key of the telematic paradigm. The virtual is the flesh of man. This is said by French philosopher Michel Serres. The holistic potentiality of telematic arts supports Ascott's metaphor of love in the telematic embrace. Roy Ascott, he was a pioneer of telematic art. Telematic embrace, says Ascott, constitute an infrastructure for spiritual interchange that could lead to the harmonization and creative development of the whole planet.
Thank you.
Thank you very much for your attention.
Thank you very much for the very inspiring talk. There are some of these aspects we can kind of reflect back to the other computer music presentations we had earlier in the conference. So let's see, do we have any questions from our audience? Okay, so Christian, so you mentioned Max. Did you use live electronics also in the telematic domain? If yes, how?
Yes, this is the key because, you know, the live electronics was using the whole time. So we never play without electronic. And so what we notice is that the electronics create a sense of spaciousness. You know, without the electronic, it's a very dry and environment, and the electronic connects. The electronic sounds connects in a much more effective way than just the acoustic sound, right, Cássia?
Yes, but I guess that he wants to know maybe the technical thing. We were using like loopback, yeah, to route Max to Jack Trip and to Zoom.
We are connected through Jack Trip, which is a software for audio communications through networks, and we routed that to Max, and we always work with the output from Max. We are always listening through Max. Does that answer your question, Christian? Okay.
Okay, great. All right, so do we have any other questions from our audience? Okay, let's see. So, okay, so one thing that kind of was interesting is that you mentioned the need to deconstruct the current visual modality based, because which has been heavily inspired by the film industry. Do you find similar sort of thing in this telematic tools, which probably based on communication?
I think one thing that we said in the beginning, we said that chamber music is a model of communication. Why chamber music is a model of communication? Because chamber music is a very sophisticated system of communication. So people are playing together, but they do gestures. They have a very vast, huge vocabulary to communicate with each other. And this is a real-time communication. And then, so I think the key of the whole work with technology that we have today, it's how we can create a very expressive and effective communication between many machines. And this is what the chamber music offer. This is said by Fischer also. That was they offer a very effective model of communications for our technological works, and that's why we consciously choose the idea of chamber music, the idea of playing together, creating music together, because this allows us to create a very sophisticated way to communicate with each other and to express emotionality and to express connections. Cássia, we want to add something to that?
No, I think is that what it's. As an artist, as a player, I think it's very important that we come here and we talk about feelings and emotions like Christian was doing before. And because I think that's the end of our art. What we want to do is to mix the machine.
Yeah, there is two things that are important. One is the idea of chamber music as a model of communication. The idea of the electronic sounds that we can shape in a way that it can also convey our subjectivity and our emotional feelings.
Yeah, so I mean, no, I'm from kind of a research technology research background. So I think it will be this kind of conference is very important for artists, through work on telematic music, kind of post kind of technical current problems that's probably based on human verbal communication. Yeah, so maybe that way we researchers can maybe come up with new research questions based on these artists' work on telematic music. And I guess we may have more questions, but unfortunately, the time is up. So we'll take, once again, let's give our big round of applause to Paulo and Cássia for this very inspiring talk.
Thank you very much.
Thank you. And so we'll take a quick 5-minute break. And we'll be back with the music database and ontology session, which will be chaired by Tojo Sensei. And so we'll be back we'll restart at 10:20. And in the meanwhile, if you're presenters for the next 2 sessions, I think now will be a good time to do a quick mic check and screen check. So thank you.
Okay, so can I test the connection? Can you hear me?
Hi, yes. So please, it'll be a good time.
音の共有はあんま聞けないですよね。音声を共有。で、
スライド見えてます。
見えてますか？ OK。あとは音声どっかでかけられるかな。
音が共有されていないようです。
そうですね。ちょっと待ってください。こっちの音はどうかな。
聞こえてます。
はい。OK です。ありがとうございます。
Okay, and Ino-san,
Hi.
Hi.
Let me share my slide. Could you see my slides?
Yes, the screen is fine.
Okay, and
Got it.
Can you hear?
動画元も yes, both videos and audio is working fine.
Thank
So
you.
I think that'll be good. So 東條先生、よろしくお願いいたします。
Thank you very much.
Tojo Sensei, I can't hear your audio. Could you check if your input device is set properly?
Oh, can you hear me?
Yes. Now,
Okay.
okay,
Sorry,
perfect.
yes. Yeah.
Okay, so
Okay.
okay, so now, はい、よろしくお願いいたします。So, Sensei, the floor is yours.
So the presentations will start at 10:20, 1 minute.
Okay.
Okay, everyone. The remaining is the very last two presentations. Good morning, Japanese friends, and good late evening in American friends, and unfortunately, the very small hours in Europe. So the first speaker is Masaki Matsubara. Could you share your screen first? Okay, may I ask you to begin?
Okay, I'm ready. So, good morning, hello, good evening. My name is Masaki Matsubara from University of Tsukuba, Japan. Today, I'd like to introduce an open dataset called CROCUS, which is dataset for musical performance critic documents. We will also report the analysis of those data to explore which contents are useful for students. This work is collaborative research with Rina, Takeshi, and Isao. Especially Professor Isao Tsuji is one of the most famous professional oboe player in Japan. So let me begin. So instructions for playing musical instruments have traditionally been given face-to-face and was considered unsuitable for virtual learning environments. However, today, due to the COVID-19 pandemic, the demand for online lessons is growing rapidly. An advantage of online music lesson is that space and time do not necessarily have to be shared, thus allowing for remote and asynchronous teaching. For such lessons, teachers listen to recordings of musical performance and write on textual feedbacks, and then return them to students. Today, some musical colleges adopt this approach. Verbal information is essential for conveying how the learner's performance sounds, why they didn't play well, and how they should practice. However, teaching using words is not easy. In our preliminary survey of 109 people with musical experience, some were not satisfied with their teacher's instructions. There are three issues. One, lack of concrete advice. They preferred instruction based on facts. Second, inconsistency of instruction over multiple lessons. And last, irrelevant wording to the performance. We believe that one of the reasons of these problems is lack of teaching protocols. Like in the other fields, we have IMRAT structure or SOAP structure in medical field. But in music field, I don't think it's generally shared. And at present, empirical knowledge of what kind of instruction is being given is not widely shared. So even among students who aspire to become professionals. So we launched a project for accumulating instructional documents from a College of Music last year. This study reports the first step in investigating useful document formats for musical lessons. And this is the introduction of our dataset called CROCUS, Critic Documents of Musical Performance. You can access this site from the link which I put on the Slack channel just before this session begins. And in the left side, there is a list of documents, and you can sort them by clicking some attributes or index. In the right side, selected critic documents will be shown. And all documents are written in Japanese, but it can be translated by machine learning translation option. So you can click the machine translation button. And you can also see the annotation of each sentences in the data, which I talk later. You can listen the recordings, see the ranking of each viewpoint and the musical scores. Let me try. So here here is the website. And we can see the tags. Tags are later explained, and you can hear some and also the scores are here. Yeah, I hope you can enjoy it after the session. And here how we constructed the CROCUS dataset by collecting performance and critic documents. So here are the details. So we asked 9 music college students measuring in oboe to record the performance of 10 orchestra studies shown in the table. As online lessons have become the norm in the music colleges due to COVID-19, we adopted a comparable situation. That is, each student played in a less reverberant and less noisy environment at home. For the critic documents, a total of 239 critic documents are provided by 12 teachers who are currently with or formerly belonged to well-known music colleges, orchestras, and brass bands in Japan. Each teacher wrote critic documents assuming the usual lessons for a total of 20 performance recordings. Here's an example of the performance. And the next one. You can hear some differences between them. And the teacher also responds a different way. So let me move on to the analysis part. In this study, we analyzed collected critic documents based on 2 research questions. First, how are the types of sentences in the critic distributed? There are differences among instructors, performers, and pieces. And the second question is, what types of sentences would be included in a useful critic? Well, to clarify what types of elements are effective for the usefulness of critical document, annotators categorized every sentence into 6 types. We adapted and adopted Simon's definitions. So this study focused on the following 6 types: giving subjects information, GSI, and giving object information, GOI, asking question, AQ, giving feedback, GF, giving practice strategy, GP, and giving advice, GA. GSI and GOI is providing some general or specific information based on teacher subjectivity or the referable events. And giving feedback is a evaluation of students' knowledge. Giving practice is providing suggestion for ways to practice. And giving advice is giving specific opinion or recommendation towards the achievement. And we asked two annotators to give tags to sentences in all documents. Yeah, here are the examples. As a result, ratio of types are as shown in the table. Most of the critique included giving advice. Of course, it's something feedbacking, textual feedbacking. And but there are a few asking question type, probably because it was an asynchronous class. And interestingly, the other ratio is very different among the teachers. The figure shows the number of types among teachers and students and pieces. We calculated the intra-class correlation coefficient, and the statistically it was confirmed that the differences in the distribution of types were larger among teachers than among students and among pieces. So for the first research question, to answer the question, answer is most of the critique included giving advice, but the distribution of types varies more by teacher than by piece or student. Let's go to the next question. So to evaluate the usefulness of the critique document, we conducted an online questionnaire survey via crowdsourcing platform. We recruited 200 people with musical experience and asked them to answer the question, do you think that this document is useful for future performance? With an 11-point Likert scale. Each participant responded to 25 randomly selected textual documents for the performance instruction. These are the highest and the lowest rated examples. The highest one has a lot of sentences and a variety of types, such as GSI, GA, GP, GF, AQ, GP, GA. And on the other hand, the lowest rated critique has few sentences and low diversity. And it doesn't provide any advice or feedback or practice strategy. Likewise, we collected and sorted into the one graph. The upper figure shows average scores of all documents. Each line indicates critique documents with error bar. And these lines are sorted by usefulness score. You can see some of rating are high and some are very low, but there is not much difference in the middle class. And the lower figures shows the average scores of the usefulness for each teacher and each student and each piece. And we also conducted statistical analysis to them, and the result that the usefulness of the critic differed more depending on the teacher than peers or students. So same as the distribution of the types. So let's compare with the distribution of the types. So comparing it with the distribution of type, we can see that teachers with high score, like C01 or C07, have not only, of course, having a lot of sentences, but not only GA, but also having a GP or GOI or GF. And also here is the supporting evidences, and the figure show a histogram of types in the best 10% and worst 10% critic documents. As you can see, in the top 10%, giving practice were observed only in the top 10. And giving advice are both cases, but GOI is more in the top 10. So to confirm these insights, we performed multi-level modeling to know which types are effective. And the model revealed a high number of description of GOI, GF, GP, GA significantly improved the usefulness. Here is a factor coefficient. So these findings would lead to better forms of critic documents where teachers are recommended to include those types if possible. And the lower figure shows the relationship between the number of types 1, 2, 3, 4 and the usefulness score of each teachers 1, 2, 3, 4, 5, 6, 7, and 12. And comparing GP and GSI, you can see when the number of GP increase, the usefulness score slightly increase. However, when the number of GSI increase, the usefulness score in most of teacher decreases. Interestingly, in teacher 11, it's increasing. So we need further analysis as a future work. So let me conclude the takeaway. So to answer the second question, what types of sentence would be included in a useful critic is a high number of descriptions of GA, GF, GOI, and GP significantly improved the usefulness. And now for future direction, we are now thinking many directions. So let me briefly introduce. So we are now thinking to extend the instruments to investigate the generalizability of our findings. And also we need to further deeper analysis, because in these studies, analysis is very preliminary analysis. So we need more further deeper analysis, like semantic classification, or sentimental analysis, or students' knowledge, or relationship between teacher and student. These are very important factors, I think. And third direction is to extract multiple viewpoints from crowds to clarify the individual difference in preference. So someone prefer the more subjective information, maybe, and someone prefer the more concrete information like that. We need to estimate the user's preference at the same time. And last, if we can find a better protocol of critique, we can implement the system that supports the writing critiques or searching critiques or personalize the critiques. That's all of my presentation. I'd like to hear the question. Thank you for attention.
Okay, thank you for your presentation. And may I ask the audience any comments or questions? If you have any comment questions, raise your hand by reactions or write a sentence in the chat. If there's no comment, I'd like to ask a question because Matsubara sensei's research is more strongly connected to the natural language analysis.
Yeah.
And I mean, that's a major in natural language. Could you show the classification, the type of the classification that is a AFGP something? This one, yes. It's based on someone's research.
Yeah, someone.
Yeah, how reliable or how convincing?
How reliable. So in the music education field, the many people refer to those papers and updated by the different teams. So yeah, how reliable? I just I rely. I use this one, but yeah, okay. So we need to verify the reliability of those aspects.
Yeah,
But
perhaps there might be several different dimensions and different ways to classify.
So in the Simon's definition, there are a lot of dimensions like moving or demonstrating or speaking or like totally 24 dimension aspects. But for the online asynchronous class, we cannot demonstrate the asynchronicity and we cannot speak in the textual feedback. So we just select 6 types.
Yeah, this is a good example. This is a GOI, giving objective information. The teacher is using some metaphor, like a duck or elephant.
Yeah.
So such a kind of metaphor can be, the same meaning between teachers and students. That is my question. As far as we are using metaphor, the information passing is not direct.
Yeah. Thank you. So yeah, in this example is not quite good, but usually in GOI, it's like in the but second that the quarter note is late or too early, like that. And in this example, this phrase represents DAC is referable because there are the textbook in the Prokofiev scores, and it's written. It is explained as this phrase is DAC. So this is not a metaphor.
Okay. Peters and Wolffs. Okay.
Yeah, Peters and Wolffs. Yeah.
Okay.
But as you say, yeah, if you use DAC as a metaphor, it's not objective. So like
yes.
We need to categorize into subjective or another, types.
That sounds like an elephant. Is some interesting comments, but is this convincing for the students or not? I doubt. Yeah, that's my personal feeling.
Yeah.
Okay. This conference, the very beginning invited talk, keynote talk is Hashimoto Sensei. He has mentioned about a Kansei work. And I strongly feel that we need to connect natural language sentences to the music feelings. And sometimes we employ metaphors and we employ some explicit, implicit, some that is a difficulty to transmit one's feelings to others. Why don't you think of a set of reserved words that is some well-defined a certain number of sets to transmit. This word is used in such a way, something, and you propose a set of reserved words, for example.
Set of reserved means, for example,
yeah, as far as we employ, that is many vocabularies, like 2,000 words. That is the mutual comprehension between teachers and students may be difficult. So when such a kind of some distant teaching, then teachers uses such and such words. They declare beforehand.
Beforehand.
For example.
That's possible. And in the real field, music education field, some norm was formed. Like rushing phrase is accelerating, and 他にないからか。Yeah, and maybe we can predefine before the class if you need. But okay, reserved word. Yeah, thank you for comment.
It's my personal opinion. Yes, exactly. That is on the last page. You have shown that is the personal difference. That is a keyword for your research. I think. Yes, some word may not be common. The same word can be used in a different way between persons. That is my worry. Yeah, my issue. Yes, individual difference. Yes.
Yeah, that is my issues too, and I need to implement devise some algorithm to capture the individual preferences. Yeah, now I'm working on such kind of technology on the other laboratory.
Have you read Murakami Haruki?
Yeah. Yes.
大理石のような声。
No, sorry. No.
But I can imagine something like that. Yes. Such a good metaphor can transmit some feelings, but that kind of things should not be used in teaching.
Yeah, so should be used more general but precise to the to embodied things or concept things.
Yes.
Yeah, if you use the surface term like musical scores term, then the students cannot learn much more.
Okay. Sorry, time is up. So we need to move up to the second presentation. Thank you for your presentation.
Thank you very much.
May I ask Ino-san to prepare for your presentation?
Okay. Wait a moment. Can you see my slide?
Yes.
Okay.
Please begin.
Okay. Hi, my name is Nami Ino. Actually, I'm not good at English, so please go easy on me, especially Q&A. Okay. Let me start my presentation. I'm going to talk about the complexity analysis of instrumental performance based on ontology structure for music selection. This study was approached from the viewpoint of knowledge engineering field, and we position this as our early research. This slide shows the contents of my presentation. The music selection is an important factor for instrumental players. If players can understand which techniques they are good or bad at and choose pieces appropriately, they can improve their performance skills. In the field of musical research, there are a number of studies for music recommendation or supporting music selection. However, when we focus on the case of instrument player selecting a music piece, we need to consider the technical aspects. Therefore, we believe that it's effective to target information about action. In fact, it's not easy to take into account the action-related information, especially from information on the music scores. Or our previous study, we developed the guitar rendition ontology that describes the relationships between guitar renditions and explains how to perform them. We thought that the perspective of rendition was useful for music analysis because it includes elements of action. For your information, several ontologies related to music already have been developed. However, it doesn't specify the style of rendition and the actions. So the purpose of this study is to evaluate musical pieces by defining the complexity of rendition on the basis of our ontology structure. This study, we analyzed traditional classical guitar etude to provide indicators for selecting music. Okay, let me explain the guitar rendition ontology before talking about etude analysis. Here, a guitar rendition ontology conceptualizes and classifies the good classical guitar rendition. As a side note, the term rendition refers to how to play an instrument. A present version modified in this study consists of 106 primary classes and 23 properties. The feature of this ontology is a detailed description of actions using these properties. This is an example of actions described in accordance with these rules. The artificial harmonics is a rendition to generate an overtone. Here. Okay, let me explain. In action 1, players pluck a string with a finger on the body side of a guitar, while pressing the same string by a finger on the neck side and touching a string with the index finger of body side. Next, in section 2, players release the index finger from string while pressing the string. It's kind of complicated. These are the improvements we have made in this study. We added several techniques that are not named or defined, and we gave the detailed names such as Tremolo 1 to Tremolo by 4 fingers, like that, and so on. And in the properties, we added action 4 to describe an action in more detail. About description of action, we improved about 30 renditions because there are not enough specification. For example, this tremolo, the order of plucking with right finger is usually thumb and ring, middle, and index finger. So description up to action 4 is necessary for each finger. So we try to break down the action into smaller pieces and describe like this. Okay, now I'm going to talk about analysis of guitar etude. At first, we focus on learners and investigate what types of rendition appear in existing etude books. There are two cases when created an etude book. One is created by the composers and another is created by players. So we try to identify the differences in renditions when etude books were created from different perspectives. We chose etude number 1 to 10 as a subject of our analysis. This table shows the list of etude. These results show the number of renditions to each etude and the information entropy calculated from them. In etude books created by composers, Blowell and Carrascoza have a similar tendency of using a full-fronting middle one. And descending through and ascending through in late number, orange. In comparison, solo was structured in such a way that these are used alternately. About Kagawa, the Japanese edition notes it's better to follow them in order because this is one composition consisting of 25 pieces. And in Blowell, he stated that this is beginning of a series of etudes that were composed for the real guitar apprentice. This suggests that the order of pieces is an important factor in their etude. As you can see, these graphs demonstrate the increase in both the number of renditions and the information entropy. Next, we took up 2 etude books focusing on soul. These books were published by famous guitarists and they include various pieces regardless of the opus number. As shown in these figures, the result differs from soul's etudes in that the overall number of renditions tend to be small. According to Segovia, this is improving student techniques or maintain advanced players technique. So it includes various renditions. About Abe, he seems the order of the pieces is important because he noted that this book is arranged in a easy to follow order. However, as you can see, we couldn't indicate his intents from only the number of renditions. Therefore, we next analyze the complexity of guitar renditions. The calculation rules for weighting properties and classes are as follows. Weighting 1 to action-related properties that represent the relationship of action, such as action and conditional action. And some actions have a restriction or requirements in describing the action in detail, such as used finger or place of action. We believe that these related to complexity of action. Therefore, we are additionally weighted. Finally, to take into account the difficulty of action itself, we weighted player's action on a scale of 0 to 3. This figure shows a tree map chart with a complexity value over each rendition represented by a area of a rectangle. I turn with the left hand, which is a subclass of ornamental rendition, was the largest value, 16. And the other renditions in the same category also tend to be high values. In comparison, the fingering rendition, percussive rendition, and note bar rendition tend to be low, ranging from the lowest value because they are basic technique run at the beginning stage. The values of articulation on rendition, called rendition, and pitch rendition and a timbre rendition were valid because they are applied techniques. For chord rendition, which requires technique using multiple strings, tremolo and rasgueado had a large area. Tremolo is an especially difficult technique that even some professional guitarists are not good at. About the 12 renditions we extracted in the 5 etched books are represented by a black box here. Tremolo and Seha are related to renditions are large value because they are relatively required advanced techniques. And staccato and spontello were small because they are required a simple action. And descending slur and adjunctura were same action, so that the complex value are equivalent. From this result, we find that the complexity value corresponds generally to intuitive difficulty of rendition. Applying them to musical pieces can be provide an effective indicator for music section. So I'm going to talk about the next stage. In regarding to guitar rendition, we think that there are 3 type of difficulty when playing an instrument. We consider the complex value of rendition as an indicator of type 1. In addition, we attempt to extract to indicate related to type 2 a little bit 3 by calculating the TFI diff, by focusing on the number of occurrence of rendition. The difficulty of etude was 10, calculated using this formula. The difficulty of each rendition was this figure shows the difficulty level of each etude number for the 5 etude books. Kagawa was relatively high and Browell was low, but both of them had a tendency for difficulty level to increase. In addition, Abe here they showed a similar tendency of the line as a Kalkashi. Yeah, this one. And as I mentioned, these authors took into account the order in which learners can easily practice. On the other hand, to etude books made by Seoul and Segovia. We couldn't determine whether the difficulty level corresponded to the etude number because the graph remains almost unchanged. In fact, there are no implicit instructions regarding the order of the pieces. Therefore, we find that our approach was somewhat consistent with the subjectivity and intention of the etude author. We need to increase the number of analyzed musical pieces and conduct subjective evaluation of the players. Okay. As a conclusion, our main contributions are as follows. In future work, we will construct a framework that enables support for music selection for various instruments. Okay, that's it. Thank you for listening.
Okay, thank you very much for your presentation. And may I ask questions, comments? Okay, Cássia, please. Oh no, this is applause. I'm sorry.
No, but I would like, if I may, I could ask her. I would like to know what was your real motivation to think about this, and if you think it would be useful that our students could, once you just analyze so well the types of movements, if we could teach the students to write for these difficulties. If we work with the difficulties in the creative way, how do you think? Is it going to be easier to play?
Thank you for your question. Okay, actually, I'm classical guitar players and I'm teaching classical guitar. Yeah, so this study is how to say? Yeah, these issues was that's I discovered in the lesson site. Okay, so you're yeah, I know this. You what you want to know, but sorry, I can't explain to more detail. Sorry. Yeah, but I just know if we construct a knowledge like ontology using action information, I guess maybe a student understand more more actions and how to practice the guitar, and teachers also understand the how to teach their actions or express their music. Yeah.
Thank you.
Thank you.
Okay. Any other questions, comments? May I ask you a short comment, short question? That is a complication, complexity and difficulty are two different notions or different thing? Complexity and difficulty are different?
Yes, different from two aspects. Yeah, that complexity is just complexity is just means rendition rendition difficulty itself, and difficulty is means in this study means for the pieces, music pieces.
Okay.
Yeah.
So did you assess the difficulty of the two actions? I mean, action 1 after action 9 may be more difficult than after action 7, for example.
Yeah.
So two renditions are connected, then the difficulty may be changed.
Yeah, you mean about reliability of the...
No. Okay, two renditions. Rendition
Two
1.
renditions, yeah?
Yes. And after one rendition, the other rendition may be easy.
Yeah.
But some kind of other renditions may be difficult. So the connectivity of the two renditions.
You want to say the the order of the renditions?
Right. For example, arpeggio after tremolo, for example.
Yeah, it's kind of complicated. So yes, in this study, we have not considered the order of renditions in details. So we need to look into that.
Okay, thank you.
Yeah.
So time is up. We'd like to cordially invite all the discussants to the breakout rooms. You can find breakout rooms at the bottom line of the Zoom window. So that is a quite informal exchange of the opinions. So I heartily invite all the attendants here to go to the breakout rooms and continue further discussion. Okay, thank you for presenters and questions.みんな著書は待ってるけど誰も行かない。 Hello, hello.
This is the closing session.
Recording in progress.
May I start? Okay. Okay, so there are please stop the speaker or microphone interval. Okay, thank you. Okay, let's start the closing session. I would like to thank you all of you for attending the conference. So that we are very happy to reach the final session. I would like to say on behalf of the committee member, thanks so much. And let's move into the contents of the last session. I would like to share the screen. Which one? Okay. Okay, start. So first of all, I would like to say about some statistics. And, some of the statistics numbers are shown here. The number of non-author registrations reached 261. The average Zoom participants are 20 to 30 for each session, as you see. But the number of viewers of YouTube Live is 40 to 170, a little larger than the Zoom participants. So I can observe that as the day go by, the number of YouTube Live viewers is increasing. So currently, the keynote speech on the first day, provided by Professor Shuji Hashimoto, gets the max number of viewers, 170. The unique viewers of the keynote speech is 100 or around. So I suppose the half of the registered people have watched the keynote speech. Then I would conclude that the combination of Zoom for real-time presentations and YouTube Live for time shift watching afterward have worked well to some extent. And since the number of people who subscribe Slack is more than 250, also Slack has worked well as the announcement channel to the all audience. Okay. The next corner is the Best Paper Award and the Best Music Award. So please present them firstly by Kitahara Sensei. So I stop the share the screen.
Hi, this is Tetsuro Kitahara, one of the scientific program chairs. Okay, so from me, so let me present who got the best paper award. Okay, okay, so. Jump! The best paper award is Deep Learning Based Music Instrument Recognition, Exploring Learned Features Representations, presented by Michael Tynes and others. Congratulations! おめでとうございます! So we, the chairs of scientific program, discussed which paper is the best for best paper award. So we made a decision based on some different factors, such as the review scores and the quality of presentation, and then the relevance to the theme of the conference. This presentation was very good, very clear, and very the quality of the research is very good. So, and all of the chairs of scientific program so strongly agreed with this paper is the best in the papers of this year's CMMR. Congratulations! おめでとうございます。
Okay, let's move on to the music award. So, Shintaro Ibai Sensei. Are you ready? Okay.
Yes. Hello. So the best music award, the best music award goes to Carl F. Gerber for the work Approaches.
We cannot hear you.
Sorry.
Turn on the microphone.
Not yet. Hello.
Sorry.
You hear me?
I was wrong.
You are wrong.
Yeah, very clearly.
Okay.
We can hear you.
Once again?
Again. Start again, please.
Okay. So the best, some of them, some of you already got to know, but anyway, I repeat again. And the best music award goes to Carl F. Gerber for the work Approaches for flute and interactive violin automation. So this work is technically and musically very rich, resulting by machine learning and also human learning, especially using parameter of physical distance between the performer and the machine is successful, since this reinforces the interactivity mentally for the performer. So congratulations, Carl.
Thank you so much. So let's move on to the next corner. I'm going to share the slide. Okay, the third corner is future CMMR conferences. The first speaker is the Aramaki-san or Selvi. Please go ahead.
Hello, everyone. Can you hear me?
Yes, we can.
Okay. So we would like to, well, on the behalf of the CMMR steering committee, we would like to say some word about CMMR 2021. And first of all, we would like to thank our Japanese colleagues for the nice and fluid organization of CMMR 2021. It has been quite a while since we started to think about the organization of CMMR 2021. Well, the CMMR in Tokyo. And I think it was maybe around, well, during the CMMR 2017 in Porto that we first started to talk about this possibility of having CMMR in Tokyo. And it was with Keiichi, Satoshi, and Tetsuro that we first discussed. And then during CMMR 2019, we finally decided that CMMR 2020 should be in Tokyo. As you all know, the sanitary crisis arrived, and we had to change the plans and to make difficult decision of canceling CMMR 2020 and to have a fully online CMMR 2021 event. After all these difficulties, it has been a great pleasure to catch up with you and the CMMR community again during this special, very special week, although virtually, and to discover your Japanese colleagues also in the local organizing committee. Although we've seen a growing amount of online conferences since the sanitary crisis arrived, and people are getting used to such meeting, organizing CMMR 2021 online was a great challenge in my respect. First of all, because of the different time zones that made it impossible to propose satisfying schedules for everyone. It was natural to choose sessions that fitted to Japanese working days, even if it meant sessions in the middle of the night for Europeans, like now when it's 3:40 in European time. So it's
it's a kind of nightmare.
It's quite a nightmare, but it's nice to see you anyway.
Thank you.
Second, it was a challenge to manage to attract people after endless Zoom meetings since the beginning of the pandemics. I think people are tired of following like conferences or meeting on Zoom, but still it's great to see that so many people connected to YouTube and to Zoom. So it's fantastic. The fact that more than 200 people registered for CMMR illustrates also the great interest for the conference, its themes and its organizers. And third was a great challenge, also the inclusion of the artistic program. And adding artistic contributions in such a setting was not an easy task. But here again, making the music program available from day one to the attendees who could visualize it whenever they wanted, was a very good choice in our opinion. So, in spite of the great freedom that an online conference offers in terms of possibilities to attend the artistic and scientific program at any hour during the whole event, such a conference cannot, unfortunately, replace a real one. In particular, the interaction after presentations and during coffee breaks and the evenings can never be the same on Zoom or on Slack. Although CMMR will be remembered as a very interesting and special event that gathered a lot of attendees, although not at the same time always, we suffered from not being able to be together and enjoy lovely Japanese food and the culture and discover your way of living. So it has always been important for us in the steering committee to favor interactions between scientists and artists during the CMMR in order to create vivid connections between people within our interdisciplinary community. We therefore want to do what we can to get back to the normal functioning as soon as possible. To this end, we plan to hold next year's CMMR in Montreal, Canada. That was the initial thought, but due to the still uncertain sanitary situation and administrative difficulties over there, it unfortunately turned out that this could not be possible. Therefore, we cross our fingers and really do hope that the crisis will be over in 2023 so that we can finally meet at last and hopefully in Tokyo in 2023, as Keiji Hirata will explain after this presentation. So thank you, cross fingers. So thank you again for a great organization, and we're really looking forward to CMMR 2023. Thank you.
Thank you for good introduction to 2023. So I have prepared some slides for the 2023 CMMR in Tokyo. So I would like to share the slide. Yes, this is the slide which I used on the first day in the opening session. So this is the missed poster for CMMR 2020 in Tokyo. This was the illusion. But now, I can reuse this poster for the CMMR 2023 we are projecting right now. And so that I would like to show you some plan for the 2023 in Tokyo CMMR. The planned conference venue is the same as in 2020. That is the Tokyo University of Science, located in Kagurazaka, Tokyo, almost the center of Tokyo. Also, we are using the music hall as the same as 2020. That is the Ongaku no Tomosha Hall. And the conference date and deadlines are not determined. But up to now, we plan to set them almost the same season or time zones as this year CMMR. So that means in November or around. So anyway, please pay attention to the announcement from our committee. Also, I hope the staff of 2021 will stay for the 2023, 2 years ahead. And probably some new committee members will join the committee, hopefully. So this is a plan for the 2023. The end of my talk. Thanks so much. And finally, I are appreciating for your cooperation and presentations and the support, many things to realize the CMMR 2021. So I'm going to call each staff out one by one. So please step into the camera frame. Can you see the camera frame? Which one is he? Sorry. Can you share the camera frame? I stop to share. Can you do? Yeah. Yes, I stopped. Hmm? Hmm? This is the Ryohata's camera. I see. Sorry. I understand your message. And please look at the sorry for technical trouble. Sorry for waiting. So first of all, the co-general chair, Satoshi Tojiro. The next, scientific program chair, Tetsuro Kitahara. music program chair, Shintaro Imai, is remote.
Hello.
He's remote. Okay. He's leaving. Okay. And finance chair, Masaki Matsubara. He's on the way to the staff room. Maybe he's in his car.
He's driving now.
He's driving now, right?
I don't know.
The next, the proceeding chair, Aiko Uemura. Oh, Matsubara.
さすがに違うでしょ。
Aiko Uemura.
上村さん。
Uemura.
いない。
We are missing Aiko Uemura. Okay, management chairs, Hidefumi Omura. Managing chair, Ryo Hatano. Management chair, Shun Sawada. Secretary, now Aoki. Okay, let's join. Then. Good. And the student technical staff, Daisuke Kurasaki. Okay, he's a really great job. And the also student technical staff, Satoshi Sekioka. And the web chair, Masatoshi Hamanaka. And
General chair is?
Who is it?
I'm Keiji Hirata.
So see you in 2023.
See you! See you in Tokyo! See you!
That's the end of the closing session. Yeah. Thank you.
Thank you.
Yes, actually, the COVID-19 disease is not over, so still severe at many places across the world. So please take care of it. Of course, I'm going to take care of myself. So finally, we hope you everyone well. See you soon in 2023 in Tokyo, in person.